Good morning, everybody. My name is CJ Dudley, and today I'm going to talk to you guys about the future of microscopy. I think most everybody in this room has used an optical microscope, but for the general population, the knowledge of microscopy beyond the optical microscope tends to wither away. My research focuses mainly on atomic force microscopy. Well, what necessarily is atomic force microscopy? Specifically, we can make an analogy that AFM, for short, is very analogous to Braille. A finger, in this case a microcantilever, feels over a surface, and we can record that displacement. Now that we have that one displacement, we can do some sort of raster scanning across this sample and provide somewhat of a 3D image by making a lot of line graphs. As you can imagine, this process is relatively time-consuming. For an area of about 10 microns by 10 microns, which is the scale that we work on, a regular line graph of good quality can take up to about half a second per line with current commercial AFM. Now, if you're going to take and do 2,000 lines, we're talking about 15 minutes per image. Well, that's pretty good if we've got a sample that's just kind of hanging out. If we're dealing with something with a faster time constant, say DNA, for example, or some sort of moving specimen, that leaves a lot to be desired by the researcher because they can't necessarily see what's happening. So we want to move faster, and that's really where my research lies in. I'm not a biologist. I don't know, about a lot about AFM, but we create these devices that allow us to move faster across the sample. Specifically, we want to move at about a rate of 10 to 20 kilohertz across this sample, allowing us to ultimately make a video of this AFM. So how can we really move that fast? Well, the principle lies in piezoelectric actuators. And piezoelectric actuators, everybody has one in their barbecue, albeit on a much smaller scale. If you apply a force to this, it produces a voltage. And then this phenomena also works in reverse. If we apply a voltage, we can get a force out of this actuator, which results in a displacement. Now, the motion of these is almost infinite, or the resolution is almost infinite. These devices have picometer resolution. But the problem is when you start moving at these fast speeds, the motion gets a bit messy. And we need something to guide the motion. And that's where the mechanical design comes in, and that we create these flexure-driven stages that allow us to take the motion of this actuator, and at high speeds it can look, somewhat like a snake, like the dance move the snake, and allow us to just translate that into one motion, the actuation direction. So what we want to do is create a stage that is stiff in the out-of-plane directions. Specifically, if we're actuating in the X direction, in the Y direction, and the Z direction, most importantly the Z direction, because we don't want to damage the sample. So we want to make it stiff in those directions, but weak in this actuation direction, so we can kind of control the resonance. So the design is focused on picking this resonant frequency that allows us to have a complete control over the device up until that resonant frequency. So my work specifically right now is in preloading these actuators. Now, why do we have to preload them? Well, piezoelectric actuators are made of a bunch of layers of this piezoelectric material glued together. And when you start moving something at such a fast speed, you end up having this large inertial mass move along with the sample. And that is going to produce a tensile force on this actuator if it's not loaded or if it's not preloaded. This ultimately destroys your stage, and we have problems. Now, typically people just take and put a screw on the back of this actuator in a device and tighten it down, but that just adds another screw or another spring in series. And we all know that two springs in series are weaker than each individual spring, so that ultimately decreases the frequency character or the capabilities of the stage. So my work focuses mainly on making a preload device that allows this actuator to operate at high speeds. So combining this good mechanical design of flexure-driven mechanisms and a good preload mechanism, we can ultimately scan at these really high speeds. So, yeah, thank you. Any questions? All right.
What you said the 20 kilohertz was the desired goal. Is that per measurement or per frame?
Yeah, we want to actually move the stage at 20 kilohertz. So each line would go back and forth, at 20 kilohertz. So the actual video rate of
Way higher than typical video.
well, that's each line, and then we have to do 2,000 lines, or we could even do a more resolution line. The actual video rate that we're looking at is like between 60 and 120 hertz refresh rate. But you want to kind of over-design this device so that this resonant frequency is far away from your operating range, and you have a really good frequency response in that area.
How wide of a field of view, so to speak, can you get with that kind of a target rate?
With that target rate, we're looking at about 10 micron by 10 micron.
And what kind of resolution?
Like Z resolution.
Lateral resolution. Let's say it's 10 microns wide. How many samples are you making along each line?
Oh, gosh, I would say 2,000 to 3,000 line scans.
How do you traverse 10 microns wide that fast?
Yeah, that's kind of the goal. These
The speed of sound?
I don't think so.
Well, it's not very just I guess.
Well, just doing it 20,000 times a second.
Yeah.
10 microns. How would that be like?
Yeah, I'd have to get back to you with a specific order of magnitude on that one, but
Just curious.
I don't think we're breaking the speed of sound in the polymer base, hopefully. So, yeah. All right.
Okay.
Cool. Thank you.